So thank you very much, Helmut. Thank you for the invitation of being here at the Institute. My talk kind of ties up a little bit with last week's talk by Silvius Klein, but I don't expect that you were there. So let's start with some ergodic space. T is an ergodic transformation, x mu is just a probability space. And imagine we're given a measurable map, say, into this, or often in applications you take the unimodular matrices, determinant 1. It's a measurable map, and associated with this ergodic space and this map, you build the cocycle. And the cocycle goes from the trivial fiber bundle to itself, so x cross Rd to itself, and it does so by mapping a pair xv onto the transformation Tx axv. And so this is what one calls a cocycle. And what happens if we map this n times, so CAT n acting on xv is Tnx, and then you have this product, and I label the product the wrong way. So you start, so from the left you take Tn minus 1 and so on. So you have that, and for a long time people have been interested in the behavior of these long matrix products. So there are some very classical, not to say ancient theorems. For example, Furstenberg-Kesten theorem, which was then later subsumed by the subadditive ergodic theorem of Kingman, says that 1 over n log, and of course I have to give you an assumption on the cocycle, I will do so in a moment, but just first a little bit sloppily, this creature converges mu almost everywhere in x to what's called the Lyapunov exponent associated with the cocycle. What is the Lyapunov exponent, and what did they have to assume? They needed to assume that this function is in L1, and the Lyapunov exponent is simply the expected value of this. So L, or rather the limit, is the limit, which, as we will see in a second, is the same as the infimum over all n of integral log. And just to save chalk, let's denote this matrix product by M. There is a reason why one says M. It's called the monodromy matrix. Why that is so is also, let's not get into that. It's very easy to see that this average here, this expected value, has a limit. And this is a fairly trivial consequence of the following thing. If you denote these numbers by an, then note that an plus m is less or equal an plus am. So we have a subadditive sequence. Why is that? Because the norm of the product is less or equal the product of the norms. And if you break this product into two pieces, right, then the second, this piece on the left is obtained by one that looks like that, but shifted by the transformation. And that's an invariant. You're assuming that mu is invariant under T, of course, in your ergodic system. So you have that, and then you just remember, this is actually a nice but tricky exercise for your calculus class, to ask your students to prove that under this assumption this limit exists. It might be minus infinity, right? But note that if this is always greater equals 0, if you have an SL dr, a unimodular cocycle, right? Because the norm of a unimodular matrix is at least 1. All right, so that was Furstenberg-Kesten. As I will not formulate the Kingman subadditive ergodic theorem. It subsumes this, but we have no need for it. There is something that this really goes with, a geometric statement called the Oseledets theorem. And in some ways, this is a deterministic theorem. It's not an ergodic theorem, but I won't go into the details of that. This is also called multiplicative ergodic theorem. Let's stick to dimension 2 for simplicity. You can formulate this in great generality. I won't do that. What it says is that under the assumption of the Furstenberg-Kesten theorem, if L is positive, then there exists a line. And for some strange reason, we'll call this line maybe script V, if I can manage. So a line in R2. So when you formulate the general Oseledets theorem, you just have this flag of subspaces, and you denote them by V. So we just have a line through the origin. This is V, with the property that 1 over n norm mn, and this line depends on x, sorry. So this is V index x, mn x, that's that, this product. Applied to a vector V, this tends to L as n tends to infinity. To the Lyapunov exponent, we're assuming positivity. I'm sorry, minus here, minus L. For all V in the line, but not 0. All right, so what is this line?
So there's some
log. This is the unique contracting direction. So if you start with any vector off of this line, you will go to plus L, right? So what is the significance of this? Well, we can easily go from here to Anderson localization, but before I do that, it's natural to ask, when is the Lyapunov exponent positive? So when is another ancient theorem from the 60s is Furstenberg's theorem that says that in the IID case, which is subsumed by this formalism, you just take the Bernoulli shift on an infinite product of some alphabet. So in the IID case, if the measure mu, maybe that's not the greatest notation, so if the single side measure in, let's do it in SL2R, that means a probability measure on the matrices, and you're taking a random product, is contractive and strongly irreducible, then L is positive. So what are these conditions? In a nutshell, there are several equivalent ways of formulating this. One kind of, look, if you take a probability measure sitting on the orthogonal matrices, they have norm 1. Nothing grows, right? So what this has to, you need two types of conditions. One ensures that you're not compact. So you can formulate this in such a way that the support of your probability measure on the matrices is not compact, okay? Another way to say this is if you take a long enough product of matrices in the support of that measure, and you divide this by the norm of that, it converges to a rank 1 matrix, which of course the idea behind that is that's some kind of expanding direction, all right? So you need an expanding direction, And the irreducibility says that there is no finite set of lines that is invariant under this measure. Okay? Now, unfortunately, and we had this discussion in Klein's talk, this proof is indirect. And somebody correct me, hopefully, if I'm wrong, but there is no way to quantify a lower bound for this L in terms of some information on the measure on the matrices. I discussed it with Klein. He says he proved something else. He proved the analytic dependence of the...
That's one thing. I vaguely remember looking at this stuff.
Okay.
Some comes dependent. But you're right, I think it's a complete generality.
So certainly, I would love to understand this better in a quantitative way, having to do also with n squared omega, which we'll get to later in the talk. But let me show you an ancient method, Herrmann's trick. Maybe we should call it a method because it's been applied more than once. No. No. And I haven't given this enough thought. But some of my impression was always that the whole literature goes in the opposite direction. You don't try, and it might be hopeless. And we should discuss this some more in relation to n squared omega, which I'll get to hopefully at some point. But Herrmann's trick...
The question is to understand the lower bound or to...
Yes.
In terms of some data.
Imagine we had some kind of effective way of proving Furstenberg.
Okay, you just want to...
Then
given the measure, can you give a lower bound?
Yes, but the question somehow goes further, because if we had an effective way, we might be able to treat case with correlations, like n squared omega. It's a highly correlated case.
I'm just asking, because that's been asked, and I think that... All right. So
okay.
I just want to understand what you think the question is.
I wish I knew better what the question is. If it often with such problems is if we have the right question, we might find the answer. So with Herrmann's method, it's a particular cocycle for which you can bring in the theory of subharmonic functions. You can just bring in subharmonic functions. And so let's take as our ergodic space the circle with Lebesgue measure, of course, and Tx is a translation, but you'll see how this is not really relevant for this Herrmann's method. And so what we're looking at, and I'll take a particular cocycle, the reason for which I should explain, but the cocycle is like this: 2 lambda cosine 2 pi x plus, say, j omega minus e minus 1, 1, 0. And j goes from n to 1. And so this is our mn. What do we have to do? We have to take the norm. Notice this is unimodular. The determinant is 1. And I will tell you why we're looking at this.
Log again, or?
Log. For some reason I forget them today. What is this? This is a particular cocycle, the Schrödinger cocycle. Let me squeeze it in here. So if you look, and this is very relevant to this talk in general. If you look at the following problem, so you have lambda Vn psi n is E psi n. This simply, if you want, a two-step recursion for the sequence psi n. N here is on the lattice, the one-dimensional lattice. And Vn should be given to fit into this dynamical framework in the following form. It should be some function f, real value typically, evaluated along an orbit T and x. All right? And notice that this fits perfectly in the cocycle language because we have here right? You're solving an ODE, So this is the propagator that takes you one step to the right. And so then you take a product of these exactly in this fashion here with these MNs. And so here we have our MN. And so now Herrmann's trick is simply to rewrite this in complex notation and to realize that this integral is the integral of a circle in the complex plane. So what he does is he introduces, let me put that here, z is e to the 2 pi I x, and say a is e to the 2 pi I omega. And if you do that, then you can rewrite this as 1 over n log product okay. And now get rid of the cosine. I'm going to write lambda z a to the j plus 1 over z a bar j minus e minus 110 norm dx. And so this is not good because you have a singularity at z equals 0, but there is a trick. Because absolute z is 1, you can multiply this whole thing by z to the n. That's Herrmann's trick. You get 1 over n. You take this inside, you have lambda z squared aj plus a bar j minus ze minus z0. All right? And now you realize that this logarithm is a subharmonic function. Because if you take this is an analytic function in Z. In fact, it's a polynomial in Z, matrix valued polynomial. Log of absolute value of an analytic function is a subharmonic function. Maxima of subharmonic functions are still subharmonic. Log norm of a matrix is therefore a subharmonic function. And so this is great to equal 1 over n, the value at 0. The value at 0 is simply lambda a bar j 0, 0, 0. So this whole thing, there is no more integral. This whole thing is equal to log lambda. And let's say lambda is bigger than 0. All right? So what this shows you is that if lambda is bigger than 1, then the Lyapunov exponent is bounded by below by log lambda. Notice that the dynamics played no role. You could have picked any sequence of numbers aj that didn't even come from dynamics. Right? But if you lose the dynamics, then the Lyapunov exponent loses its meaning as an almost everywhere limit of these. You don't have a Furstenberg-Kesten theorem, all right? So now let me discuss a little bit that this is sharp, as amazing as it is. So many things can be said about that. Tom Spencer here with Soritz some years ago noted that, of course, this method applies to trigonometric polynomials, but it depends on the highest power, the coefficient of the highest power. All the others are killed. So therefore, if you take an analytic function instead of cosine, you have a problem, because then your highest power, the coefficient, tends to 0. But they found a way to make their theorem is that if you take an analytic function and lambda is large enough, then the Lyapunov exponent is still positive. I already made the remark that the dynamics here really doesn't play much of a role. So for the future, and that's the skew shift, let's note that if you can put, if you put j squared, j cubed, any power of j, which on face value doesn't come from dynamics, but in fact it does if you add more variables, the method still works, right? So let's talk a little bit about the spectral theory. I just erased this guy. So we have an operator. This is a hugely studied operator. And so what are the spectral properties? This is called Harper, or almost Mathieu. The reason it's called almost Mathieu is because The Mathieu operator, which has a periodic potential, is the case of omega rational. So if omega is rational, it's a reduced fraction, then this is, you have a periodic potential. And then the true monodromy matrix, remember we had used this word monodromy before, is the propagator that takes you q steps to the length of the period. So then you will have mq, this is the propagator of length, if you want. Q equals the period of your periodic potential. It is SL2R because you have we just observed that, Schrödinger cocycle. So therefore, what does the ancient Floquet theory tell you? The characteristic polynomial, the eigenvalues of this determine the entire spectrum. The determinant is one, so only the trace matters. And this is called the discriminant. It is the trace of MQ as a function of what? I'm a little bit imprecise here. As a function of E, the energy, because what you're really looking at is you're looking at an equation, an ODE. And this ODE. And so this trace is a function of E, forget x, put it 0. And then there is this classical picture. You have these two lines, minus 2, 2, because you have to solve a quadratic equation that has this in it under the root, okay, for the eigenvalues. And the picture is like this. I won't belabor this point, this is ancient, all right? So the trace goes between these lines, it cannot turn around inside. The spectrum consists of the projection of these bands. This is the E-axis. This is the graph of this over the E-axis. These are the bands. These are excluded. It always comes here from the upper left. And what are the eigenfunctions? What are the solutions to these? The psi n are of the form an e to the I, k of e, and this k of e has a fancy name. It's the quasi-momentum. And the eigenvalues of this are precisely e to the plus minus I ke. Ke is real if and only if e is in a band. And so in these forbidden zones up here, ke has a non-zero imaginary part. You will then get exponentially growing solutions. That's not in the spectrum. The spectrum consists of these bands. So if you are irrational, then you fall into this framework, this Furstenberg-Kesten Cocycle type framework. By the way, you do have a Lyapunov exponent in the periodic case, but it has no meaning as far as I understand. Right? You can integrate, of course. You can do Herrmann's trick all you want. You get positivity. All right. So if omega is irrational, then the following results are known. So if lambda is bigger than 1, we saw that L is greater to equal L of E is greater to equal log lambda. This is actually this positive. So this is an equality if E is in the spectrum of Hx. Okay, that is a theorem, I think, that Jean Bourgain and Zhytomyrsky proved this as a result of some industry that I will have more to say later, about 15 years ago, maybe 12 years ago, that you have equality of the spectrum, it's strictly bigger. If lambda, the sign of lambda doesn't play any role, but let's just make it positive, then L of E is 0 on the spectrum of Hx. I forgot to say,
Is this almost right?
yeah. I forgot to say that this is a fixed compact set. This is some fixed compact set K. The spectrum doesn't depend on X. It's easier to see that it doesn't depend on X almost surely. Okay? And to see that, you notice a covariance property, namely that Tx, that's the same as Hx plus omega, is unitarily equivalent with Hx, because x plus omega on the circle corresponds to shifting the lattice by 1 unit. So this is, you have this covariance relation where u is the shift on the lattice by 1 unit. I won't say whether it's left or right, because that's confusing. So whatever it is to make this correct. And once you have this unitary equivalence, you basically see that the spectrum is invariant under the shift, all right? So this vanishes, but it's of course strictly positive of the spectrum of Hx. And to see that, so why is this? This follows from Kotani theory. Kotani theory says that the absolutely continuous spectrum is the set, which is a closed set, is the set where the Lyapunov exponent is 0. All right? When lambda is 1, that's the transition, this phase transition, the spectrum is purely singular continuous and the measure of the spectrum is 0. There is a lot known, really a lot known about this Harper operator. There's even a formula for the measure of the spectrum. As far as I remember, what is it? 2 times 2, maybe it's 2 times 1 minus lambda. Rui, do you remember? 4 times 1 minus lambda. That is the measure of the spectrum of Hx. All right. What I should say here is one has Anderson localization in this case. That's a classical, by now classical paper by Zhytomyrskaya. So what is Anderson localization? And what is Zhytomyrskaya's theorem? For this exact Hx, Zhytomyrskaya in the 90s proved that for Diophantine, this means not well approximated by rationals in the usual sense. So n omega is greater or equal some constant n to the a, where a is bigger than 1. So almost every omega satisfies this with some positive constant c omega and all n. Or you say it satisfies this for all large enough n with constant 1, the same thing. Diophantine omega and almost every x, then Hx has or exhibits Anderson localization. Anderson from Princeton University, Phil Anderson. So what is Anderson localization? It means, i.e., there exists psi x, psi jx, j is in Z, is an orthonormal basis. So Hx diagonalizes with an orthonormal basis of exponentially decaying eigenfunctions. That's what this means. So psi is an orthonormal basis of eigenfunctions, and they are exponentially decaying, and not surprisingly, they decay at the rate of the Lyapunov exponent, so e to the minus ln, maybe up to an epsilon. All right? Is it clear what this says? So the spectrum is, as one says, pure point. There is no absolutely continuous. There is no singular continuous. The spectrum is the closure of the eigenvalues. The eigenvalues are highly random, quote unquote, where the entire source of randomness is only this x. So this x here is your only source of randomness. So that's why often these types of models are called Schrödinger operators with deterministic potentials. They're determined just by x. Nevertheless, these vary in some very chaotic fashion in X, as do the eigenvalues, but the closure of the eigenvalues is a fixed compact set, namely the spectrum. All right?
Does it really depend on X?
Yeah, strongly, yes.
Not depend on X, but the phenomena. There can be X's where...
Yeah, they're bad X's, yes. So now, let me give you a wrong proof of Anderson localization. All right? It's always fun to give a wrong proof. So the way this works is we have Kingman, Furstenberg-Kesten Kingman's theorem, and we have the Oseledets theorem. So by these general soft ergodic theory principles, we know that if you look at h x psi is E psi, then we can find, and we write this as a cocycle. So then we find two lines. Let me use colors. So we find a red line and a yellow line. If I can find, first I have to find colors, then I can find lines. All right. So we have, in the original Oseledets, as I wrote it, we had one line, and we called it V, but now and Vx, but I'm going to put a plus here, because that gives me the contracting direction in the forward direction. But then I have another one, Vx minus, which gives me the contracting direction.
This all depends on E.
Yeah, very good. Yes, yes. So this depends on x and on E. So is everybody clear on what these two lines are? So that means, this means that if your initial condition psi 0, psi 1 falls here, then this decays exponentially in forward direction. Similarly, if this falls here, then for negative n going to minus infinity, you decay exponentially. So when do you have Anderson localization? If and only if the two lines coincide. So if they are the same, they coincide. What if they do not coincide? Then you cannot decay in both directions. In fact, you must grow exponentially in one direction, correct? But then there is another general principle, which is no line going on, this Schnoll-Simon theorem, that almost surely with respect to the spectral measure, if you grow exponentially, that energy does not belong to the spectrum. Conclusion, we've proved localization, haven't we? Because either you're not in the spectrum or these two lines coincide and then you decay exponentially. Which trap did we fall into? That's what Peter said, that E dependence. We have also, there is a measure zero set of this fails. Kingman and Oseledets. You have to eliminate the measure zero set. So then you have a continuum of measure zero sets on which you lose control. So for that seemingly technical reason, this is not a proof of localization. Localization is much harder. And it is a game of resonances. You have to keep track of resonances and you have to kill infinite tunneling. Let me give you a little bit of a...
Well, in fact, if you make your, if you replace your Diophantine condition by something irrational but very well approximated,
then it's false, yes. So Liouville case, it's false.
But this, even for the random V, where I guess
Yeah. Yeah, you need more. You cannot just do the soft stuff, because especially in the random case, you do have a zero probability set where the convergence breaks down, where Oseledets breaks down, and so on and so forth. So let me give you a slightly strange, perturbative argument of what we might be trying to do. All right? Now, imagine that you make here lambda huge, but you renormalize. You divide by lambda, and you write this as a matrix. Then you get a particular kind of Jacobi matrix, if you want. You get the potential on the diagonal, and you get epsilons on the off diagonal, where epsilon is 1 over lambda, right? And so call this matrix H for Hamiltonian again. Well, maybe I shouldn't call it. I'm running out of names. B, X, epsilon. And X here is where the Vj's are given by, for example, cosine. So exactly that. And now, if epsilon is 0, then, forgive this triviality, we can diagonalize, right? All the eigenfunctions are deltas sitting at lattice points. Now, if epsilon is small enough, in fact, you want.
Something I don't like about this one. Let's say so.
Say it again.
What happens if you were doing the continuum with d2 by dx squared? This would be a bit trickier because you can't treat this as a perturbation of a diagonal. Right? I mean, does it work in that case?
The continuum case is completely different because then you're unbounded, the spectrum is unbounded.
It's still true that if you have a random potential, that it's localized. So I'm saying it's the part of your argument I don't like.
Okay, so
does it work in the other case?
this naive logic will not help you in the continuum case.
What you do is you just break the theory up into dirichlet blocks.
Well, you have no
That's
choice
work.
because the energy can be unbounded.
Oh,
So you see
You
here,
do the same thing.
the energy is always bounded.
You just have to change the scale.
So here the energy is bounded because when I divide by lambda, I know my energy will remain bounded. It can be at most lambda large. But indeed, in the continuum, I have unbounded spectrum. But so allow me to just be discrete. So if Vj minus Vk is much bigger than epsilon, and you take the min over j different k. I'm just saying that look at the mutual distances between the Vj's. If epsilon is smaller than those, then it will still be true that the by trivial first order perturbation of eigenvalues, that the eigenvalues will be close to these delta spikes that you had for epsilon 0, plus corrections that decay exponentially away from there. All right? But now what if you have a coalescence? And that's what's called a resonance. So what if you are here in a picture, and this is, I've heard Sinai speak about this. He always draws this picture, and he has his forbidden zones and his resonances. I will get to that right now. So this is the graph of your potential function, and then you translate this by omega. So this would be the original cosine, called v of x, Morse function with two monotonicity intervals, and then you have the shifted version of itself, and you have an intersection at x naught. And so let's look, for the sake of argument, and all of this is extremely trivial, I realize. I hope I'm not boring you terribly. So look at this equals 0. The solutions will depend on x, and E of x will be 1/2 V of x plus Vx plus omega plus minus the square root of the difference plus epsilon squared. And if you look at this near x naught, what you will see is that these eigenvalues actually do the following thing, that they form these quadratic arcs, and then this is what Sinai calls a forbidden zone, all right? And so this is the classical phenomenon that occurs at a resonance, where the coalescence of V of x with the shifted version, with another element of the diagonal, that's called a resonance. And this ideology applies in a much wider sense. But let's see what this means on the level of the eigenvalues. So in the epsilon equals 0 case, you had two delta spikes, one at 0 and the other one at 1. If this happens, once you turn on epsilon, this is no longer true. You will have, let me draw it in red next to it, you will have an eigenfunction which is a combination of these two, and then you will have an eigenfunction with the reverse sign. So where again you have this spike, but you see, so you have plus plus, and you have minus minus. Is that clear? Out of two delta spikes, you make an amalgam, you combine them. And so what we're really staring at, and this is difficult, I admit, is to carry this procedure through over larger scale. This is exactly KM type theory, if you're familiar with that. So there is a KM argument that you can do, and Fröhlich Spencer Witt Sinai did this in the 90s, where you prove localization perturbatively for large lambda for such functions, such Morse potentials. by passing to larger and larger scales and controlling this process of resonances. So what you could imagine is that at the next stage, two of these now larger supports, those could resonate. Then you get something with 4 spikes. And if you do this infinitely many times, you would have an extended state, which is not exponentially localized. So I was planning on presenting the Bourgain-Goldstein theorem, but maybe I don't really have the time for that. Bourgain-Goldstein theorem says, let me just write down what it says. The statement, yes. So it's completely different. This is perturbative. You make lambda large, epsilon small, same thing. They just assume that the Lyapunov exponent is positive. And let me cheat here. I will just put F here. And their theorem says so theorem this is from 99. It says assume that the Lyapunov exponent as a function of omega in E is positive, and you take an inf over all omega in E. Just like in Herrmann's method, he gives you that. And what kind of f do you have here? F is, for example, a trigonometric polynomial or an analytic function on the torus. Cannot be constant, because then the Lyapunov exponent would be 0. Okay? So it's automatically a non-degeneracy assumption on f. Assume this. Then, for almost every omega in S1, Hx exhibits, let me just put H0, Anderson localization. So that's how they formulate their result. They freeze x, so you just put x equals 0. And then for almost every omega, this operator exhibits Anderson localization. And that means exactly that you have it diagonalizes through an exponentially decaying family of eigenfunctions. And how do they do this? There are 3 ingredients, really. There is LDT, so Silvius Klein mentioned this in his talk, large deviation theorems. Right? Analytical ingredient, you use subharmonicity and almost invariance of these monodromy matrices that we had on the board, but you also use semi-algebraic sets, not just a notion, but results. You use Seidenberg-Tarski theorem, projection of semi-algebraic sets are the same, but with the degree of these sets being controlled by the degree of the original one, and you use Milner's bound on the Betti numbers, in fact, just the connected components. Why you do all this is perhaps a bit mysterious. Somehow this semi-algebraic set theory limits the complexity of the creatures you're dealing with. And that allows you to somehow mimic some random independence. Yeah? There is one cute step that I'm just taking out of context completely here, but it's really a lovely little result about measures in the plane, or rather just measurable sets in the plane. And after the talk, I'm happy to fill in all. They,
That's an assumption.
that is an assumption. They don't say how you get this in a concrete. If lambda is large, Sorit Spencer tells you that it's positive. Yes, yes. Their theorem applies, and that's actually important also for higher dimensional tori. All right? So you can look at the multi-frequency case, and that filled a big.
There's
in
always
the definition of the potential, not in the Schrödinger form.
Okay, so there is the PDE case. So we're in the.
The PDE case.
No, so what you just brought up is there is also the quasi-periodic PDE case. That theorem doesn't apply to that. We have theorems for the PDE case. They are completely different in the sense that you don't have Lyapunov exponent, but there is something else going on. They cannot be true for almost every frequency vector. There will be a small set of bad frequencies, but positive set, and then the disorder has to be made very large depending on that smallness. Right? You can never eliminate a small set of bad frequencies. Here they managed to get rid of a measure zero set. So that lemma of theirs has an extremely clean formulation. You take a measurable set in the square, and you imagine that every horizontal, so this is the omega axis, and this is the theta axis, which x is here. Omega is our omega, right? And imagine that each horizontal line intersects S in at most m intervals. So at most, S intersect the horizontal line Lx is the union of at most m intervals, I, little I, where I'm allowing empty intervals, right? So at most m intervals. That's that limits your complexity. And then it says that if you take very steep lines on the torus, so they wrap around, okay? Very steep lines, where L is on the order of n. So this is really a set of omega in 0, 1 with the property that omega L omega hits the set S for any L which is between n and 2n, say, all right? Then the measure of these omegas is at most n cubed, the measure of S to the 1/2, plus m divided by n. And so the idea is that if you have limited complexity, that's where semi-algebraic sets come in, on the horizontal direction, and the measure is small enough, that's where these large deviation theorems come in, then all of this will be small, provided n beats m by a lot. And how do you use that? That kills off those omegas that lead to double or multiple resonances, where you cannot kill the infinite tunneling, cannot prevent infinite tunneling. What's the logic behind this? Suppose a very steep line were entirely contained inside L. Then the left-hand side would have measure 1. This cannot happen because then a horizontal intersection would have n intersection points. So for a line omega L omega to be contained entirely inside of this set S, right? You would need n intersection points, but you have at most m. That's the logic behind this. All right, so let me go, and I'm happy to explain in as much detail as I can why this is relevant to localization and how this works. So Jean Bourgain has written a book about this around 2004. It's this orange book called, what's it called? Green's function estimates? Rui, what's it? Okay. So let's talk a little bit about the skew shift. So from Peter's question about ODE versus PDE, I gather that the PDE case is more interesting, and
it's Tom who thinks so.
And
I mean, Spectral was-
I understand. So the PDE case is truly,
That is a true Anderson localization.
yeah. But nevertheless, the ODE case still has some fascinating problems, and one that you should care about a lot, Peter, because it's the skew shift model. So it looks like this. You get xy goes to x plus omega x plus y mod z2. And omega is the Diophantine. And this is called the skew shift. The skew shift is supposed to have better ergodic properties than the shift. But it cannot on the face value of it, because in this slot, if you take a set that only depends on this slot, then you are as bad as the shift. In particular, you're not even weakly mixing. So the skew shift is not weakly mixing. Nevertheless, if you look at the cocycle, the Schrödinger cocycle over the skew shift base, and you take a function, ideally the cosine, that depends on the interesting variable here, you will find this. So j omega plus j choose 2 omega minus e minus 1, 1, 0. And so let me formulate a conjecture that as of now is not known. So you build your Lyapunov exponent, you take norms, and you take the expected value. So you integrate dx dy. Then the conjecture is this converges to L, of course, omega E. You have an underlying base dynamic, so all of this Cocycle theory, Furstenberg-Kesten applies. Yeah, so the conjecture is that this is positive for all E, that's very important, all E, and all lambda not zero. And I just killed off a matrix entry. And so then why is it conjectured that this should, by the way, how am I doing on time?
We're doing good, 10 minutes.
10 minutes. Why is it conjectured that this is true? That's a good question. It's not really, it's not so easy to get any straight answers why this should be true. One thing is that you notice, in contrast to the Harper model, which is still there, what really goes on because of this here, or at least it seems so, is that we're looking at the fractional parts of j squared omega, and there is this philosophy that these points should be close to random. There are much more sophisticated versions, also results, for example, by Peter and Rudnick and Zaharescu, that address the Poissonian behavior of this. So what is Poissonian? If you take n points at random, randomly, uniformly in the circle, then it's easy to see that there is some Poissonian behavior lurking in the background. Namely, count the following thing. Count how many j's have the property that xj falls into 0 lambda over n. All right, this is what I want to say, I think. L. And then the probability that this happens converges to the Poisson distribution. So you have, how does it go? E to the minus lambda, lambda to the L over L factorial. Am I making a fool of myself? I don't think so. So this is easy. This is Bernoulli, and that's the regime where the central limit theorem does not apply. It's the rare event, the Poisson limit theorem. But in the paper by Rudnick, Sarnak, Zaharescu, this is formulated differently via level spacings. I won't go there. So if we had some kind of, this is what I was trying to say before, if we had a better understanding of Furstenberg's theorem in a quantitative fashion, also allowing for correlations, maybe we would have a chance somehow relating this reference, which is very poorly understood, to this Lyapunov exponent. We do not have.
Can I ask, maybe you or Peter about this? If the j squared omega of omega is irrational, one knows that the spacings are possible?
No. So Peter, but so in their paper they make some Diophantine assumption on omega. In fact, you have a sequence of rationals with prime denominators. I shouldn't be explaining your paper.
We show certain statistics, but it's very hard to do this. I'm sure it is.
You're sure it is?
Although I've seen it. He thinks you need infinitely many parameters to prove anything statistically, but then you have only one parameter.
Well, that is a problem.
I even believe if you take omega squared. Let me ask. So the point of that conjecture is any lambda.
Any lambda, but also any E, because remember what we because in the Harper model you have 0 on the spectrum.
Right, and you also have, isn't there some, in that Harper model, models like that, the linear thing, you need, lambda small can be different. I mean, isn't there something?
There is a phase transition, lambda bigger than 1, you have localization, positive exponents, less, they exponent 0 on the spectrum, positive off of the spectrum.
So it's as if that sequence is, even though it's cosine, j squared, omega, it's as if that's random, right? Because the Lyapunov exponent is the same, actually, numerically.
Yeah, but this philosophy of j squared omega being random helps very, very little with the Lyapunov exponent. Right?
By the way, if you take j omega, the linear thing, that is not Poisson.
No, that has a totally different behavior. So what is known? about 15 years ago, Bourgain-Goldstein and I, we showed Anders localization for the skew shift, so for this, but with, loosely speaking, with n squared omega, but that's also a lie, because this doesn't come from dynamics. There is no dynamical system. So what you do is you do ny, just like here. Ny, and then you can leave it like that, because the n choose 2 and n squared omega is the same. You can absorb that.
Again, why is that not the other? What's the difference?
So this doesn't come. So I say if you just add this, it's as good as that, because you can divide omega by 2 and you take the linear piece into the y. Right? So we proved that for if you give me a tiny epsilon, and then we can make lambda huge depending on epsilon, and we throw away a small set of omegas, then you have Anderson localization. But remember, Herrmann's method gave you for lambda bigger than 1 positive Lyapunov exponents. So what I've been busy with, and I'm extremely happy to be here working with Marius, Rui, and Fan, the three of us have been trying for months, beating our heads against the wall, but with some success, of understanding this conjecture, working towards it. I'm pointing at the wrong thing, not Poissonian, but okay. And
Lambda is large again.
lambda bigger than 1, Herrmann gives you positive. The point of this 15 with Bourgain was Anderson localization, which is much bigger than positive Lyapunov exponent. But now we make lambda small, and Jean was really infatuated with this problem, and being who he is, he of course got something out of his infatuation, and what he got was that for this skew shift model he was able to prove if you give him a tiny lambda, then he can take a tiny set of omegas, which is not just small in measure but also small in size, these omegas, and he gets a small positive set of energies where he proves localization, and he knows that that's in the spectrum. So the spectrum has positive measure. So that's in stark contrast to n omega, the Harper model, where we know that you have AC spectrum. There is no localization. So he proved that there is a difference between shift and skew shift. So there are several projects going on with Marius, with Rui Han, we're both here. We developed an effective version of the method to some extent that we had 15 years ago, where we took exactly this equation. We took f up there to be the cosine. We took omega to be the golden mean. And then we wanted to know in this inductive procedure that I cannot explain, it uses the avalanche principle that Goldstein and I developed, and which Silvius Klein spoke about here not long ago. It's an inductive procedure. You build up from one scale to the next. We made this completely effective with all constants. And the origin of this project was discussions we had 15 years ago with Jean Bourgain, who complained on the one hand that our method was not effective. He said we always write C everywhere, constant C, 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 C. Well, in fact, we didn't even do that. We wrote this, all right? You don't want to write C. No, this, you can pretend that you're not writing C. Yeah? And so completely ineffective. And the annoying thing about that is you don't know what the size of the initial scale is where you can start your inductive vehicle. Right? And there was some discussion, could we use a computer to verify that some finite matrix product here, say n is 10,000. Well, then maybe with a computer, if you know what you're doing, you could check that for 10,000 matrices, the product behaves in some good enough way so that you can feed this into some rigorous, effective analytical machine. So what we found out, unfortunately, is that, where am I? That the machine as it stands requires you kind of to start at this scale, 10 to the 200, outside of any computability. But we did much more than that. We described also a way to build up from small scales to that scale through finitely many steps, and I won't torture you with that, but it gave rise to an interesting, I think, new model where we look at everything over finite fields. So we switched for reasons that I don't really want to get into, having to do with this effective project, that we look at the field with p elements, p a prime, and we replace the translation by omega by a translation by congruence q, and the skew shift becomes fp squared and your omega becomes q over p, roughly. And what did we do? We looked at the monodromy of length p, the period, and we take this, we take the trace, and say for this both shift, skew shift. So let's start with the skew shift, because that's somehow the case where we understand nothing or very little. And we take the expected value over x and y in the finite field in fp squared. And what we would like to see is that this grows exponentially. In fact, we have reason to believe that it grows like e to the constant, positive constant, lambda squared p, when lambda is small and p is a prime. And how do we do this? We do it basically in the style of statistical mechanics. So we write down the Dyson series of this. Because each matrix, these MPs are of, and we do this for energy 0. So you might be disappointed by that, but energy 0 is in the spectrum of Harper. So there the Lyapunov exponent is 0 for the shift. And Ruihan and Fan Yang have done amazing work for the finite field shift model to check that the Lyapunov exponent should be truly 0. So to check that for the shift, this expected value of the trace is bounded, and it looks very promising. We've been working on this since beginning of January, after we kind of put this to the side. And so the amazing thing is for the skew shift, so what do you find if you write down the Dyson series? You end up with an expansion of the form. You have an exponential sum. Let me write this down. So you will have ai j I squared. Let me just take the first one. A1 lam j squared plus a2 k squared q over 2. EP is just the additive character in the finite field. And we sum here over j1 between p and 1 and k1 between p and 1. And we have a condition. We have the condition here that the indicator, we are only allowed to j. This is j1. This is j squared. This is k squared. Sorry, I'm a little bit out of time. So then we have we have a hyperplane, which is just a line. A1j plus A2k is congruent 0 mod p. And we have to sum over A1 plus A2 is 0, where A1 and A2 are in plus minus 1. This is the coefficient of lambda squared. And you will see that it starts, so this is like 1 plus constant lambda squared p. And this is the coefficient of lambda squared. And you will see it gives you a p, just like you want. Because the only way to solve for this congruence, first of all, A2 is minus A1. So here you have just a j squared minus k squared. This congruence can only be solved if j equals, actually there is a minus, if j equals k. And then here you get 0. So then you have exactly, they have to, only diagonal contributes, you get exactly p. So then we go to lambda 4, lambda 6, and in each term you have such a complicated exponential sum, complicated in the sense that it has ordering. We know that if you kill the ordering, then you get what you want. You get exactly this kind of growth. So now we're struggling to estimate these exponents, not just estimate. We want to say that they're positive. They have these coefficients of the, only the even powers of lambda contribute this, we know. Yeah. So, sorry. Thank you. I'm just excited about this.